Good morning, everyone. Thank you for joining that talk. So just now we have seen from Wayne and Vitaly a great tool that I decided to use. I will show you some use cases and hopefully it is going to work. So a little bit of background about me. I'm an IT security specialist or InfoSec specialist before cyber became famous. I'm heading the offensive team at DBS Bank, and I'm part again, equally of the computer emergency response team. I'm passionate about InfoSec in general, but particularly about fighting cybercrime, preventing and also responding to incidents when it happens, unfortunately, and I like to analyze malware. So, cybercrime is a serious matter, but hopefully today we are going to analyze some in a safe manner. And nobody was hurt in this presentation. There was no real incident for those that are wondering. So, about the plot, far away on the internet, it's not very far, but on the planet, it's in the middle of nowhere. My friend called me, and it's of course on a Friday at 5 or 6 p.m. Just before I was closing my laptop, I suddenly received a call. And my friend Patrick noticed that there was something a bit special about his computer and was asking for help. Because he's very far away, he was asking me if I could travel, and of course it was not an option, or at least not in a reasonable time. Or he asked me if I could troubleshoot everything by phone, and it's not easy trick, it's not so simple. Or he wanted to call Sherlock Holmes. So I told him, don't worry, I'm going to help you, let's do it together. So Vitaly just presented that in July 19, at the Null Security Meetup group in Singapore, special interest group, he released the tool called BitScout, and he was searching for a poisonous needle. So it picked up my interest. I said, it looks like a very interesting tool. Why don't I try it? So as you can see, July 19 till today is not long ago. So I've worked many hours with the help of friends and Vitaly in particular, and hopefully the demo is going to work. So as Vitaly has briefly explained, basically Patrick is located far away. He's booting up an ISO file that I've provided to him. So I sent him over Flying Pigeon because it can carry USB drive, and he was able to put the USB drive on the computer and boot it up. He also authorized the mounting of the disk in read-only so that I cannot tamper with the evidence in case law enforcement agency wants to take over from here. So I'm going to go to the demo one now, and it's going to be completely live. It was not working until minutes ago, so hopefully together we are going to make it work. All right, so I'm doing everything over virtual machines because I was not confident doing it over the network for today. We have tested several times and it works well in the network. The setup was my machine connecting to the VPN, and the infected machine was connected to VPN as well. And even over 4G connection, it was pretty smooth. In other words, I didn't acquire the disk, I didn't acquire the memory. Everything was done remotely, and that's why it was fast. So I've mounted the disk. Actually, there's one mounted too much, but doesn't matter. So we can see evidence 0 is the full disk, and evidence 1 is the partition, the main NTFS partition of the disk. So what I'm going to do is, where's my cursor? So I'm going to connect to the machine. So let's say over VPN, but for like I explained, it's local for now. I'm going to create a folder that's going to be useful for later. All right. I have access to the disk, so I could mount the disk. So I'm going into to root mode, but as Vitaly explained, it is a virtual root. So even though I have full access on my container, I cannot do anything on the evidence at least. So I'm going to mount the disk. That the disk is located in dev host evidence 1. So this one is the partition, the main NTFS partition of the infected machine. And I'm going to put it as mount, but because it's read-only, I have to specify all right, so if I indeed go to that folder now, I can see documents and settings, I can see program files. So basically this is my partition. All right, but it would be good if we could boot up that system because many of my forensics tools are actually running on it. Sorry. All right, so I'm going to create a backing file for the image. Okay, so I created a QCO file that the virtual machine is going to use. I'm going to copy a very long command to basically create my virtual machine. So this creates a virtual machine, and in fact, the virtual machine should probably be booting up by now. And I realized that I forgot to set a password for the VNC. Yes, and I also forgot to all right. So my virtual machine by right is starting now. So I'm going to connect to it. Oh, it is not starting. Okay, I'm facing some difficulties. I think I'm going to jump straight to the demo too. Sorry about that. Yeah. Okay, so hopefully this one will work better. All right, so my virtual machine is created. Basically, it's a machine where we discovered there's something wrong, but we couldn't find any evidence on the machine. So we suspect that there's a rootkit, and when we started Gmer, which is a tool to detect rootkit, we detected that the MBR, the master boot record of the machine, had been tampered with. So let's try to analyze the MBR as it is booting, and hopefully we are going to find something interesting. So, all right, so this is going to be, I'm setting up some breakpoints on my virtual machine, and as I'm debugging it, and basically, what? Yes. All right, if I'm not looking at the right one, it doesn't help. All right, so we can see that the MPR actually is loaded at 7C00. It is the bootloader of the BIOS that is starting this. Then we can see at the bottom of the screen in 7C3F that there's a function where the code is going to be relocated. So I'm going to put a breakpoint on that location. All right, so we can see that the code has been relocated in 97C40. Then I'm going to continue looking at the code. We can see in the code just listed above, in the middle of the screen, there is int13. So int13 is actually an instruction. Okay, sure. Yeah.
Hello. Check. So, sorry for interrupting this, but I'm just feeling bad for my friend who spent a lot of time making the demo. And I know it's super hard to use GDB and show live demo and comment what's going on at the same time. So on his permission, I'll just help him to comment what's going on with while he was doing, he'll be doing all the work, all right? You don't mind?
Please,
thank you.
So basically what you see, the idea is that we're going to debug the MBR, because we know that this is a bootkit installed. This was detected by some tools. And what Nicolas just showed, this GDB session was attaching to the virtual machine that starts from BitScout, from the live CD. Okay, so actually QEML comes with the GDB server, which you can attach to, and you can debug starting from the first instruction of the virtual machine code. At 7C00, this is the magic address where BIOS of the virtual machine puts the MBR code. That's why this magic value, okay? So at 7C00, you will see the first instruction that is exactly the same on the hard drive and the first byte. So what Nicolas said about the relocation is that, of course, as far as the MBR is infected, it has to execute the original code at some point, and that's why they are migrating code to a different place, to this 97C00, where they continue execution while restoring the MBR, the original one, to let the Windows boot as nothing has happened. Sorry, please go ahead. Do you want to comment? Or
well, so like I mentioned earlier, the ENT13 is the interrupt to read the file on disk, and it's going to read 3D sectors, so to be multiplied by 512, and it's going to load the additional bootkit data in the memory.
That's right. So just like Nicolas said, the additional data is going to be loaded because it's not going to fit into small 1 or 2 sectors from disk. So there's extra package payload which is encrypted. So that's 3D hex sectors that are read with interrupt 13. So what is this?
It's XOR decryption. So this is encrypted?
It's already decrypted, right?
No.
XOR decrypted.
Yes.
Okay. Can you scroll up? The city. No.
So we see the
So
the same location before
Yep.
Encryption, and then it was decrypted. So because it's a complex bootkit, there was at least a first level of encryption, and it was over XOR with a key that was moving according to the sectors.
So basically the payload on disk is encrypted with a simple XOR algorithm. So the first stage is you have to run it, to let it decrypt using the own XOR decryption. And this is where you can dump the next stage, but it's not yet over because there will be other layers inside.
So in fact, we discovered that there was a layer of RC4 or something that looked like RC4 encryption. It was not exactly the same when we looked through the code. I'm not going through the code, but it was near identical.
So it's a modified RC4 actually. The key scheduling was a bit different.
And so in fact on the screen now you can see we recovered the key, and it was part of the whole sequence, and we can see on that line here SYSTEM, then null character, then M, so system M, capital M.
I think it's system OM.
Sorry. Yeah. So now we managed to get the RC4, so let's decrypt the data. So this was the data that we decrypted, although it shouldn't be bytes, but it should be instructions. So let's correct that.
So after RC4 decryption, that has to be allegedly executable code if everything worked, if the demo guys are with us. You need to put the location. So we'll now try to deploy this in instructions.
No, sorry. Yeah, so actually it was encrypted.
This is the encrypted data. Okay, this doesn't make sense.
Yes. Whew. Okay, so now it's decrypted, and we can see some code that kind of makes sense with jump and calls to further functions. So we were facing one problem. Basically, what happens is the malicious MBR is going to identify some drivers started by Windows, and in that case it was acpi.sys. It's going to patch this driver to load its own malicious instruction. And because the Windows is already started, hanging halfway, and there's, we don't have knowledge of the structure of Windows, then we were not able to set breakpoint with the traditional method. So we step through the code and we identify that at some function, even though we couldn't put breakpoints, we were able to put like a cyclic jump. So basically we put an instruction that once executed is going to jump over itself again and again. So it is not breaking the code, but the code is not doing anything for a while.
It's actually infinite loop on itself, so the loop instruction. And we do that, it's so-called poor man breakpoint, because, and it's super useful here, because if you don't use it, if you put the normal breakpoint, the software interrupt, for instance, then the code will be placed to a different memory location, because you are switching from real mode to the protected mode. And you have to survive, right? If the code has relocated that interrupt 3 for the debugger, we actually crash Windows. That's why we need to use this funny
infinite loop to catch that moment when we are already in protected mode to keep on debugging the protected mode from this attached debugger.
Right, so we are putting that breakpoint and running. So Windows is already starting because I interrupted the, I crashed the machine earlier than I need to start normally. And then hopefully soon after our breakpoint is set, hit, sorry. So I'm going to continue after we patch. So the cyclic jump is EBFE.
So this is actually patching. You can see EBFE, those who read in machine code, I'm sure everyone. This is the infinite loop on itself. Jump to self.
So when Windows is starting, at some point, it's just not going to do anything at all because it's
and
patched.
now it's switched to protected mode already. This animation, allegedly, I think it's a separate thread that is rendering this, while we are running in an infinite loop in another place.
So since we managed to hit the breakpoint close to the drivers, we were able to locate it and eventually dump this driver. So now what I can do is okay, we can see there's 11K drivers, so we can see what kind of drivers is it, what kind of file it is. It is a PE executable file, so it is indeed something that looks like working. What I could do also is to MD5 this driver. And for example, I can see on VirusTotal if there's a hit.
Well, Nicolas is looking at VirusTotal. I just wanted to comment here, like, why do you need to follow all this procedure to get to the driver? Is we start from the MBR. This is a reliable point where we start execution of the malicious code, right? And we want to follow and see how it unrolls. However, it has multiple layers of encryption. This one has 3, so it's XOR encryption, RC4 customized one inside, and inside there's a container with a driver which is decrypted only in protected mode, only after it switched to the protected mode and injected into one of the drivers, ECPI.sys, only then it will run that code that will self-decrypt. And we want to catch this moment to dump it on disk, and that's what we did.
So as we can see, VirusTotal already knows about this file. Several antiviruses identify it, as you can see. But if you see, it's called Sednit for Yandex.
Sednit or Sophacy or Fancy Bear. If you have it on your machine,
it's bad.
It's really bad.
It's a bootkit with kernel-land rootkit and user-land rootkit that is typically used by the APT28 actors. All right, so it is the end of my second demo that worked much better than the first one. The first one, basically, I wanted to demonstrate that.
But you have still 6 minutes.
I still have 6 minutes.
Let's do it. Let's do it. Come on, let's fight with the demagogues on stage.
All right, so
let's support Nicolas. So, while Nicolas is recovering, just wanted to add a few comments. Like, what's the difference between the booting of VM that I showed the previous presentation and this is that he boots it right from the live CD on the remote location. Given that you have enough of RAM that you can use to boot like this, I know already the third operating system on the same hardware, then you can do it, you can play with it remotely. Where it is helpful is, for instance, the network bandwidth sucks. And you cannot actually redirect, disk reading operations over the network. Because booting Windows actually takes about from 500 to 600 megabytes of data transfer over the network. If you have a slow link, it's not an option. It's much better to connect over VNC to the remote VM. So this is where it helps. The case where I can use the setup that I showed is useful where you have a very small RAM, and you cannot actually start a virtual machine remotely because of the constraints of RAM size. Then you can do over the network, given that you have fast connection. So at his demos, he's starting all these machines right on the BitScout instance running.
So I've created already my my QCO file, my backing file for my virtual machines.
And again, the changes are not written to the hard drive of the owner, right? It's written in this temporary file, which exists only in RAM. You power it off, like no changes are done to this machine.
Okay, so copy this. As you can see.
So QEMU, when it starts with VNC, you have to set password manually, like through the monitor command. By default, it doesn't allow you to connect without password.
So now we can see that when, is it the correct Windows? Okay, now
It's
we can see
now.
Windows booting.
Yes. So we now pass the stage where we failed.
So I'm going to create.
Leaving it to you.
Thank you. So Windows is still booting, which is good. Okay, it's a bit slow, I don't know why, but let's see. So the machine is infected. That's why I put a red background. Over Samba, since we have full control over the virtual machine, then I was able to install it using apt command because it's a Ubuntu-based virtual machine. So I apt install Samba. I mounted a remote drive that allow me, for example, to upload all my tools, and hopefully they're inside. Okay, they're inside. So I'm going to look at it's over VNC, that's why the screen is not very beautiful, but at least it is executing at the real time of the server. So if the server is fast, then it should be quite fast as well. All right, so the entry point was that there was some connection coming to that machine, and we couldn't explain it. So by using TCP view, we are going to see all the network traffic passing through it. And particularly, we will see here that there is on port 1337, there is a process called CTFmon that is listening. All right, so let's try to find this CTFmon process. So if I use Process Explorer, okay, the demo gods are really not kind today.
Let me just stand on stage.
Thank you. work. So we can see CTFmon is indeed started, but if we try to see where is it or what it is doing, we can see that it was started from a non-existent process. So in other words, it exists, but we don't know who started it.
Can you run it as administrator so that you see all options? Maybe
Absolutely.
That's so the thing is that we want to know how it started, who started the process, right? Like where the infection comes from. That's why this chain of like which process started what is important. We have to restore it. Okay, at least you have the command line.
Yes, we have the command line, and so we can see indeed CTFmon started something and started on the process.
There is a port number that we recognize, right, and reference to another file.
Yes. So I don't think I have time. Okay. So I would have started a sysmon, and with sysmon, upon reboot, sysmon will have shown all the process starting, all the creation, and everything. And I would have seen particularly that it was started from a legitimate Windows DLL.
Can you show the WTR file that we've seen? Because just to jump ahead, the WTR file is actually the file, the DLL that this is a loader that loads the DLL past the parameter. The same DLL, the same loader that I showed you during my demo. But if you go to the Windows folder where it was called /WTR 9001, right? Search for WTR files. It's not there. So it means the file was deleted, it's gone, possibility, or we are dealing with the rootkit right now. So how can we check if this is a rootkit? We have to look at the same system from a different angle, independent of the infected system, right? So we have to access the file system and see if the file is really there. We are wrapping up. Don't worry. Just last thing to show. So we can now mount the device independently from the bitscout because this apparently is not infected, right? It's safe. And then we can look at the file system from the angle of the bitscout to see if there's any files that has this name. All right.
And so finally, we can identify the file that was just hidden, so yet another rootkit on the Windows machine. And yeah, it was...
This is another reason why you should do actually offline forensics on the machines. You should not rely on remote forensics that runs an agent on the infected system, because you will not see things like this. You will never discover these files otherwise.
So just as a conclusion, I didn't know anything about remote forensics. I didn't know anything about debugging QEMU to find a bootkit, let's say 2 weeks ago, with a lot of work and a lot of perseverance. I was able to do that. So in other words, the message that I want to pass today is that work hard and eventually you will succeed. Maybe not on stage under pressure, but other than that, yes. Thank you very much.
Thank you.